Hey there, Year 10 mathematicians, Mr. Herman here, and this will be lesson 4, Exponential Growth and Decay, exercise 3K. This will be the last lesson for the index laws unit. The learning goal for this one is to see how percentage increase and decrease link to exponential growth and exponential decay, which we'll look into what exponential means, and to also look at the formulas to work out the amount if it either grows or decays as a percentage rate per time frame. And the success criteria for this one is to be able to write an exponential rule for a word problem and to be able to apply it. To get a better intuitive feel of what exponential actually means, I've got this example here that I've just created at the top of my head, and it talks about two different towns. Okay, we'll call them Town A and Town B. How creative is that? Town A and Town B. Now, Town A has a starting population of 10,000 people. So this is town, and there are 10,000 people within this town. Now, this also applies to Town B as well, which is also 10,000 people. So we've got these two towns, okay? 10,000 people in Town A and 10,000 people in Town B. Now, here we have this word growth underneath both of them. This just talks about how much people are added into each town, okay? Now, for the growth for this Town A, I set as 300 people. 300 people. My gosh, let's try that again. 300 people, there we go, per year. All right, so 300 people added into the town per year. And the growth for Town B is 3%. New people per year. Now, I should say 3% of new people from the previous year. Okay, and that holds significant information for how many people are added into the towns each year. So let's look at the very basic one for year 1 for 300 people per year. In year 1, we have 10,000 plus 300. So we have 10,300 people. Pretty straightforward. In year 2, we have 10,300 plus 300, which is 10,600. And then you can kind of see the pattern, 10,900. 10,900. Yep. People will be in the third year, and this trend will keep happening. Okay, this trend, you're just adding 3 people because this is the growth that has been established or determined, 300 people per year. So this here is what we call linear growth. It's called linear because the amount of people that are added, it creates a pretty much straight line if you were to graph this as population growth. So we start at 10,000, and as each year goes by, we're adding 300, 300, 300, and this keeps going up in a straight line. Okay, and this is why it's called linear growth. Nothing changes. Okay, we're not adding more people to this growth. It's a consistent growth that keeps going and going and going. And the reason why I pointed that out is in order for you to understand exponential growth, we've put this growth as 3% of new people per year based on the previous year. So what we're going to do is I've gone ahead and grabbed my calculator out, and we're going to find out what 3% of 10,000 is, because this is the growth rate. 3% of new people will enter the city based on what the previous year is. All right, so after 1 year, for year 1, to work out 3%, put it as a fraction form, 3 over 100 times that by 10,000, and this is 300, okay? And I purposely chose this number so we know that it's similar to the first year. So we have 10,000 plus the 300, which is 3% of the 10,000. So again, this is going to be 10,300. Nothing too tricky. But the growth rate then, because it's still 3%, to get year 2, we have to figure out what 3% of the previous year will be. Now, because we're in year 2, we have to then rely on the previous year, which is year 1, and find out 3% of 10,300. So we're not getting 3% of 10,000. We've got a new amount now because the 300 have already been introduced into this first year. So in this case here, we're going to work out 3 over 100, but this time we're going to times it by 10,300. So now we have 10,300 from the previous year plus 309 new people. So now the rate of how many people are going in per year has changed from 300 to 309, which is 9 more. And that makes sense because if there's more people that are going to be put into the town, and we're going to take a percentage of that new amount, we're expecting a higher growth rate in this case, a growth rate amount. So in this case, this is going to be 10,609. And then again, we're going to figure out 3%, but we're not going to figure out on the initial or the starting value or year 1. This time we're going to get 3% of 10,609. And then again, we're expecting more people. So in this case, 3 over 100 times 10,609. Make sure you press the SD button. And so we have 308.27. We can just round that down to 308. 318. So let's add the 10,609 people and add 318. So 10,609 plus 318, we have 10,927. 10,927. Now, I know these examples seem arbitrary, but the main difference I wanted to show you is that if you compare the population of year 3 in comparison to, year 3 for the first town, there's 27 more people. Now, does not seem that significant, but if you were to keep going and going and going and keep going, after say about 30 years, Town B will have a significantly amount of more people in comparison to Town A, because as more people enter the town, you're going to take 3% of a greater number, which entails more people moving in. This is what's called exponential growth. So if we were to graph this very roughly, if we were to graph this by year and population, so we start at 10,000, it might seem like it's gonna start linear, but as the years go by, it curves up. Because as more people enter the town, 3% will be taken on that new people, and it will keep going and going and going, and it will exponentially grow. So what I'll do is I'll cut it short for this video. This is just a main concept of exponential growth, and decay works the same way. It will decrease or go down, either population or whatever context you have. But we'll look into that in the next video.